All right, so Andrew, your question was about chloride. How could chloride lose an electron? It doesn't want to lose an electron. Chloride absolutely does not want to lose an electron. You know, it doesn't want to lose that electron because chloride has an octet, and it's quite happy as is. How do I know chloride doesn't want to lose an electron? One of the ways I can determine that chloride doesn't want to lose an electron is I look for the stability of chloride. Sorry. You know, if you're talking about losing electron, you're talking about redox reaction. Well, how stable is chloride in relation to the other species? This is what you guys need to do. You guys need to go over to this chart and then read it once in a while. You read it once in a while, you get yourself familiar with a wide variety of species and their redox properties. And so if we look at chloride, you know, chloride's right around here, which means it's what? Stable. Well, on this side of the chart is what? The on the side of the reducer. Right. And so on this side of the chart, which means chloride is exceptionally weak reducing agent, which means does it want to lose electrons? Absolutely not. Look if chloride is harder to oxidize than water. Oxidize means take the electrons away, right? It's supposed to be harder, but you guys know the exception. The exception is chloride, because the kinetics would be easier, but they're about the same, you know? They aren't that huge, there isn't that huge of a difference. And so this means chloride is very stable. Very stable. So it doesn't want to lose an electron. Unless a very powerful oxidizer comes along to strip it of its electrons. And so what would have to come along to strip chloride of its electrons? Yeah, fluorine could, you know, because it's a tug-of-war. If there's a tug-of-war between fluorine and chloride for the electron, who's going to win? Fluorine's going to win. But chloride's not going to be happy, right? And it's going to form chlorine. Chlorine, is it a stable? You know, if you think about chloride versus chlorine, is chlorine, which is the product of that, stable? No. It's not like water, you know, unreactive like water. Okay. Anyway, this is what we call factual knowledge, because anybody can look at a table and say, this is higher than this. It's like a number line, right? Anybody could look at a number line and say, oh, +1 is greater than 0, you know? But this is beyond the number line thinking, because you have to input some memory into your brain to put some kind of relative context to this. Because if you can't put these numbers into any kind of context, then you know, it's nothing special. You know, basically, you're nothing special. You can easily be replaced by a machine, right? In science, that is. And so what you have to do is, when you start looking at these things, you have to start thinking about, you know, putting things into some kind of context, some kind of perspective. Okay? And that's good. You are, because you're thinking, okay, chloride, it doesn't want to lose an electron. Absolutely, it doesn't want to lose an electron. All right, other questions? Okay. I can't remember if this was my. All right, what we're going to do today is we're going to look at a little bit more redox and then jump into next chapter, chapter 6. Actually, a little bit of redox, a little bit of acid-base, and then go on to the next chapter. I already talked about skeleton redox. But I didn't talk about skeleton redox and basic solution, so let's take a look at some skeleton redox. Actually, let's go to advanced. One thing you'll notice about skeleton redox is this. You know, this equation is not balanced here. Actually, let's point the screen in here. All right, you look at an equation like this, it's not balanced, but one of the nice things is, take a look at this equation, it gives you the products. You know, up to now, you know, most of the stuff we've been doing, we had to predict the products. It was blank over here, and you had to figure out what was going to form. But one thing all skeleton redox reactions have in common is the major products are given, like this. So for example, iron 2 and dichromate. What do you think is going to happen when you mix iron 2 and dichromate? You're going to form iron 3, chromium 3. You know? Or here, major product given. There's only one major product here. Kind of an interesting redox. Here, you see this? Major products are given. Actually, it does want the advanced. Let's scroll down to the advanced. Those are the basic problems. Let's see if we have a... some advanced ones here. All right, so let's take a look at some of these here and maybe do some. These are an acidic solution. An acidic solution were the steps that we had covered before. In Chem 4, this is what you cover. So you can just follow the same exact steps that you used in Chem 4, come up with the same answer here. However, in Chem 4, you don't do basic. Did anybody do basic solution in Chem 4? No. And so with basic solution, you have to do one additional step. You know, typically when we do reactions, we can do it in acidic, basic, or neutral conditions. And I got a lot of questions yesterday at the chart, you know. On the chart that we had, you know, what was at the bottom of the chart? Water was at the bottom of the chart, but was it really at the bottom of the chart? You know, how perceptive were you with the chart? Did you notice that? Did you notice that there were two charts in one? That often happens, you know, and they don't give a lengthy explanation about how to use this. They figure you'll look at it carefully and figure out how to use it yourself, right? And so that's why I didn't give any explanation. I wanted to see, you know, what you guys found. The water is not at the bottom of that chart, you know, because they divided it into two separate charts. Why they do that? Well, sometimes you're working under acidic conditions, sometimes you're working under basic conditions. That's why. And so let's take a look at some of these. Actually, let's look at which one should we do? All right, let's do C, 78C. That's a good one. Sometimes when you do redox, you know, because of the conditions, for example, it's hard to predict. You know, when you're burning something, let's say you're burning something, can you predict how much carbon monoxide is going to be produced? You know, let's say you wanted 100% carbon monoxide. You don't want any carbon dioxide. And so let's say you have your stove at home. You want it to be a carbon monoxide producer to test your carbon monoxide alarm or something, right? And so you have a gas stove. You want it to produce carbon monoxide. How are you going to do it? How are you going to make your, you know? Well, you adjust the conditions, right? You can adjust the combustion conditions. Maybe you don't add as much oxygen. Right? Or let's say you want to get rid of the carbon monoxide. You know, you just want just trace levels of carbon monoxide because you don't want to be poisoning yourself at home. Carbon monoxide is a very serious poison. And so what would you do? You got to make sure your burner has plenty of oxygen, right? And so as you change the conditions, the products change. And do you think it's easy to calculate this theoretically? What do you think? Well, we can do some calculations theoretically, but right now, is it easy for you to figure out? No. And so oftentimes, and like I said, theory can get, because there's kinetics involved, there's other stuff involved. And so the theory part and doing these kinds of predictions, can get very tough. And so what's often done is you just do it by this. They have these little mini reactors. And in these mini reactors, they'll have 1,000 little cups. And in each of those cups, they'll just alter the conditions slightly, the mixture or other factors. And so what they can do is they can test a whole bunch of different conditions rapidly and see, what forms. And so this is just mix it and then see. And so mix it and analyze. And so you just mix this together and analyze. For example, here, this is one of the reactions that came up earlier, is methane. Methane combusts, right? Here. So what if I mix some methane and some ammonia? Does ammonia burn too? Yeah, normally when you burn ammonia, you're going to produce what are called NOx, oxides of nitrogen. And so we do this, we'll add some ammonia into the mix and some O2 and then analyze the product. I don't know, did I talk about this? I don't remember if I talked about this in this class or the other class. And so this is a reaction that occurs earlier in chapter 5. Or was it chapter 4? No, this was chapter 4. Yeah. Do you recognize this reaction from chapter 4? Obviously it's a redox reaction, so we can guess what one of the products, what do you think one of the products is going to be? CO2. And then another product? Water. Yeah, good. And probably NOx, right? But look at 9C here. Under these conditions, write a balance equation that represents 9C, chapter 4, the reaction of methane, ammonia, and oxygen gases to form gaseous hydrogen cyanide and water vapor. You see, under certain conditions, we don't burn the methane all the way to CO2. Under certain conditions, you have a certain balance of reagents there, a certain temperature. It burns it, or it reacts to form hydrogen cyanide. And so, yes, of course, you want to avoid those conditions. Here, I don't want to be spraying ammonia into my flame in case hydrogen cyanide is produced, right? And so this is a case where, okay, what you do is you just mix it and then see what happens. And so this is a case of what we call skeleton redox. Skeleton redox, okay, now what we're going to do is we're going to try to figure out what we call the half reactions of this. What's the oxidizing agent, what's the reducing agent, etc. And so in this particular instance, what do you think the reducing agents are? What do you think the reducing agent is? And what do you think the oxidizing agent is? Well, probably O2 is probably the oxidizing agent. And so what we'll do is we'll do this via the skeleton redox method. This is a good one to start with. We do the skeleton redox so we can get a better idea of what's happening. And so on the skeleton redox, what's our first step? We divide it into two equations, two half reactions we call them. And so what are the two half reactions we're going to divide this into? Well, we look, where does the carbon end up? In HCN. So the methane ends up in HCN. That's where the carbon ends up. Where does the nitrogen end up? The nitrogen ends up in HCN. So it's the carbon and the nitrogen. Hydrogen and oxygen, we never really worry about, If there's hydrogen and oxygen, like these hydrogens, And so that's one half reaction. And then where does the O2 end up? in water. And so these are our two half reactions. Now we can get a better idea of what's happening here. This oxygen to water, we've seen that before. Have you seen oxygen to water? Yeah, if you go back to the redox chart, maybe I should put the redox. Let me put the redox chart up here so it's easier. We don't have to look back. But take a, you guys got to look at these charts carefully. Everybody always asks me, oh, if it's bottom right, that means this. No, you look at the bottom right of this chart, and you compare it to the bottom right of this chart, and what do you see? It's different. So, oops. Email, that's it. So we've seen oxygen to H2O before. And so looking at this, you see oxygen to H2O. If I have oxygen to H2O written here, I'm not going to bother going through the steps. I know it's going to be this. It's going to be O2 plus, just read it off, O2 plus 4H plus 4 electrons yields 2 H2O liquid. But do I see methane and ammonia goes to hydrogen cyanide? No, I already know it's not going to be on there because I've already read this chart so many times, right? And so I could save time this way. Don't waste time. You know, think about exams. You know, if you're on an exam and you barely even looked at this chart, how much more time is it going to take you to find things? You know, and that's critical, like at UCLA, because the exams are so strictly timed. You know, if you want to be, well, anyway, going to this, what we have to do is we have to do the balance all elements other than hydrogen and oxygen. So we got one carbon, it's checked. We got one nitrogen, we got one nitrogen, that's checked. If it wasn't, then we balance by changing the coefficients. And then we balance the oxygens, but there are no oxygens, right? 0 O's, 0 O's. And then we balance the hydrogens. So we have 7 hydrogens here. We have 1 hydrogen here. That means we add 7 protons, and then we balance out the charge. We got +7 on the right, +7, and 0 on the left. So we add 7 electrons.
36.
Is that a 6H?
6H. You're right. 6 plus 1 gives us 7. Right. So it's 6H. So that's going to make it 6 electrons. Thanks. All right, so basically it's this. Our oxidizing agent is the oxygen. I asked you to underline both, but what we're going to see is something a little different. Our oxygen and H+. Our reducing agent is methane and ammonia. You know, it's good that, you know, when you oxidize methane, it doesn't always produce CO2 because it allows you to make new compounds, you know, new things by changing the conditions. We aren't stuck in one reaction. So methane and methanol are what they call chemical feedstocks. They're used to synthesize new chemicals or existing chemicals. All right, next what we do, once we have the two half reactions, we just combine them. And so here, except we got to combine them such that the Yeah, electrons cancel out. And so I have 6 electrons here, 4 electrons here, so it looks like 24 I need. And so I'll multiply this one, or 12? Oh, 12 is better, you're right. 12 is better. So I'll multiply this one by 2, 2, 2, 12, 12, and this one by 3. 3, 12, 12, 6. And then I'll combine it, you know, because I have the 12 electrons here, 12 electrons here. So 12 electrons are consumed, 12 electrons are produced. The electrons must cancel. If the electrons don't cancel, then you did something wrong. If you do something wrong, just back up and start over. And so combining these two, I'll get 2. So I put this running out of pens here. 2 methane plus 2 ammonia plus 3 O2. Do you see the 12H pluses? 12H plus is produced here. 12H plus is consumed here. So the 12H pluses also cancel. Let's get rid of those. 3O2 yields 2 HCN plus 6 water. Now how can is there a way to double check this? Yes. Do you know how to double check this? You check to make sure it's balanced. Right? 2 carbons, 2 carbons, 2 nitrogens, 2 nitrogens, 8 plus 6 is 14 hydrogens. 12 and 2 is 14 hydrogens. 6 oxygens, 6 oxygens. Atoms are balanced. Then you check the charge. 0, 0, it's balanced. So this looks good. That looks good. Now we assign the oxidizing agents and reducing agents and figure out the driving force, right? And so let's do that here. What are the oxidizing agents and reducing agents in the 4 direction? Well, we do that from the half reactions. Do you see these 2 guys here? These 2 are losing electrons. So this is what we call the reducer. O2 is gaining electrons. So this is the oxidizer. HCN is what? Going backwards, HCN does what? Consume electrons. So going backwards, HCN is the OA. And then water going backwards loses. So this is the RA. And this reaction happens. If this reaction happens, that means we're going from stronger to weaker. And so this tells us that you know, HCN is a weaker oxidizer than O2. No, HCN can go both ways. Normally when I think about HCN, I think about it as a reducing agent. But, you know, it could react in either way. Just like water. You know, water can go either way as well. You know, oxidizer or reducer. All right, so this is an example of a skeleton redox. This would be hard to predict. These are reasonable products, right? So we could. So redox can get complicated as well. All right, so let's go and look at a.
How do you know that this reaction will happen? You just assume it's going to happen?
I'm sorry?
How do you know that this reaction will happen?
How do I know this reaction happened? Because all skeleton reactions are observations of experiments. I don't know this reaction is going to, I couldn't have guessed it initially. It just happened. That's what they did. They mixed it together and see what happened. Skeleton redox is, it's already happened. All you're doing is you're just tidying things up at the end. You know? This is the difference between predicting the products and then just mixing and observing. And so this is just mixing and observing. So let's mix and observe something else. Which one was I?
78C.
78C?
Yes.
All right, let's do 78C. This is under basic conditions. Under acidic conditions, this is all we do. You know, we just go through those steps. Because if you think about it, why is there a difference between acidic and basic? It's because how we balance the hydrogen. The steps that we follow to balance the hydrogen, we balance the hydrogen by adding H+, but is H+ stable in base? No. And so we have to correct that. And it's a simple correction. All we do is we convert the H+ into water, actually. In base, there's plenty of hydroxide. And so it's pretty straightforward. And so let's do 78C. (78C) is, name it for me, CRI3. Chromium 3 iodide plus hydrogen peroxide yields chromate. What's IO4 minus? No. Peridate. So this one, the reason I want to do this one is because it trips up a lot of people. So we're going to divide it into two halves. So where does the chromium atoms end up? In chromate. Where do the iodine atoms end up? In peridate. And so the first one is this. Chromium 3 iodide goes to chromate and peridate. But the thing that trips people up is this. Where does the hydrogen peroxide go? But we don't care because hydrogens and oxygens are easily balanced in skeleton redox. And so it just goes to something. We'll figure it out. And so this one, let's go ahead and balance this one. We have one chromium, so it's balanced. 3 iodines and 1 iodine. It's not balanced. What do we do? Oh yeah, we change the coefficient to 3 here. All right, and then we balance what? Oxygens. So we have 0 oxygens and 8. So actually 4, this is 12, 16 oxygens. So we need 16 water. And now we balance out the hydrogens. We have 32 hydrogen and 0. And so we add 32H+, and then we balance out the charge. It is 0 on the left and -2, -5, 27, +27, right? And so we need to add 27 electrons. Here we could do a quick double check. How would we double check this?
Wait, repeat. Plus 27.
Oh, maybe I made a mistake. -5 plus 32 is plus 27. -27 gives me 0, which has to balance. The left side is 0, so I got to make the right side 0. Electrons are negative. So if I take 27 positive charges and add 27 negative charges, it comes out to 0. I balance out the charges by adding negative to one side or the other. I can't do it any other way. Well, we do a quick check. Are the atoms balanced? 32 hydrogens, 32, 16 oxygens, 16, 1 chromium, 3 iodines, 3 iodines. Atoms are balanced. Check the charge balance. 0, 0. -2, -5, +27, -27, 0. So it's balanced. So this is a balanced half reaction. What's happening? What are these? The oxidizing agent or the reducing agent? It's a reducing agent. So this is what I mean by kind of drawing a line. That's a reducing agent, right? And so this must be our oxidizing agent. So let's take a look. So we balance out the oxygens first. We got 2 oxygens, 0 oxygens. So we need 2 waters. And then we have 2 hydrogens, 4 hydrogens. So we need 2H plus over here. And then we have plus 2 and 0. So we need 2 electrons here. And so do you see that hydrogen peroxide and H plus, this is our oxidizer. It's our reducer. Okay, what do we do next? Well, actually, let's just double check that they're balanced. 4 hydrogens, 1 oxygen. That's right. I erased it. 2 oxygens, 2 oxygens. Plus 2, minus 2, 0, and 0. So that's good. It's balanced. So. All right, now what do? We add them up. So this one's going to be a little bit more as far as numbers go. We produce 27, we consume 2. So what should it be? 54. So let's go ahead and change this. 32, 2, 2, 6, 64, 54. Now I got to make this, so I'm going to go 27, 54, 54, 54. Okay. So we got that, and let's get rid of some of these. We have 54 electrons here, so let's get rid of that. We got 54 electrons here. What else can we get rid of? We can get rid of the H pluses. We have 54 H pluses, so let's get rid of 54 of those. That leaves us with 10 over there. And then the waters. We have 32 here. Let's get rid of all 32. And then we're left with 22 here. All right, and then let's add it up. So I'm going to get 2 chromium 3 iodides plus 27 hydrogen peroxide plus, that's it, yields 2 chromates plus 6 peridates plus 22 waters. All right, now let's see in the reverse direction. In the reverse direction, what's our OA, what's our RA? In the reverse direction, do you see our OA? This is going to be our OA in the reverse direction because it's consuming electrons. I crossed it out, so it's a bit messy. In the reverse direction, our RA is going to be water because that's what's giving or producing the electrons over here on the left. And so this is our OA. This is our RA. This is our RA. This is our OA. And so what this tells us is that hydrogen peroxide is a stronger oxidizer than chromate and peridate, and that chromium 3 iodide is a stronger reducer than water. We already know there's a driving force for this reaction. Except there's a problem. Actually, there's no problem here.
They're not balanced.
Oh, it's not balanced?
No.
Yeah, you're right. It's not balanced. So what did I do? I forgot the 10 H pluses over here. Now is it balanced? I forgot the 10 H pluses. The 10 H pluses are going to be OA. So these two are linked together. Is it balanced? Yeah. Let's take a look. So 2 chromiums, 6 iodines, 54 hydrogens, 20, 44, 54, 54 oxygens, so that's 8 plus 32, 54 oxygens. So the atoms are balanced. Let's check the charge. 0, -4, -10, plus 10 is 0. So 0 and 0. And so it's balanced there. I think we're set. Except there's a problem. What is the problem? The problem here is this is in basic solution. Is strong acid stable in basic solution? No. So we need to change that. And so in basic solution, all we do is we neutralize this. And so this is the extra step. We just do 10 hydroxides. In base, there's plenty of hydroxide. And so we can have any amount of hydroxide necessary to neutralize all the acid. Otherwise, it's going to turn into an acidic solution. But if I do this, what's going to happen to my atom balance? Yeah, the atom balance is going to be screwed up. So if I add 10 hydroxides to the right side, the easiest way to keep it balanced is to add 10 hydroxides to the left side. So I add 10 hydroxides to both sides of the equation. That way I don't mess up the charge balance and I don't mess up the atom balance. All right, so when I do this, what's going to happen is these are going to convert into, so I'll get 10 waters over here. And these don't convert into anything, so I just have to add 10 hydroxides and tack it on here. And so the overall reaction is going to be 2 chromium 3 iodides plus 27 hydrogen peroxides plus 10 hydroxides yields 2 chromates plus 6 periodidates plus 22. Actually, 22 and 10 makes 32. So I'll just combine the 2 waters. 32 waters. All right, so that's it. So that's. All right, so I covered basically the reactions. I skipped single replacement, but you don't really need single replacement if you do the general chart method. I pretty much covered the reactions except for one. What kind of reaction didn't I cover? Lewis acid base. So should I cover that now?
I'm just really confused how you got like the electron charge out. Like, say like if you were to count the, that's already changed.
All right. How about this? This is neutral, so no charge.
Yeah.
And then each one of the H's is +1. You have 4 of them, so this is going to give you a total positive charge of +4. Here. And then this is neutral, so the total positive charge is 0. So the total charge is 0.
You add 4 electrons.
Yeah, the only way to balance this is by adding negative. So do we want to add electrons over here? No, because that's going to bring us to a negative charge. So we have to add electrons here to decrease the positive charge. How many electrons do we add? 4. Each electron has a -1. So -1 times 4 gives me a -4. +4 plus a -4 gives me 0. That's what I want. Now they match.
But
And so that's what I'm doing. I'm just counting it up like that. me, all right, we're going to do just a brief. Lewis is going to be covered more in depth later. So let's look at a Lewis acid. CO2, what are some of the chemical properties of CO2? It's stable, yeah. It's not that reactive. Greenhouse gas. Is it a good metathesis reactant? CO2 really participating in metathesis? It does as a decomposition product from carbonic acid. Otherwise, not really. What about Bronsted acid base? Bronsted acid base is a good proton donor? Proton acceptor? No. Redox? Yeah, I showed CO2 as a redox. Remember I showed it? CO2 is an unusual one because CO2 is a little bit of a paradox because they use CO2 in fire extinguishers, right? But CO2, as far as redox properties, would be considered an oxidizer or reducer? An oxidizer. Is it a strong oxidizer or a weak oxidizer? So think about if you have a fire, let's say a wood fire, would you want to fan the flame? When you fan the flame, what do or blow on it? You're adding oxygen, more oxygen. You're feeding the fire, right? They call it. And so oxygen is an oxidizer, so you're adding more oxidizer to the fuel to get it to burn better, right? And so if you're trying to use CO2 to put out a fire, isn't that like feeding the fire? Aren't you just adding CO2? Isn't CO2 just like O2? A powerful No, O2 is what we call a powerful, strong oxidizer. CO2 would be considered a very weak, extremely weak oxidizer. In fact, we really don't think of CO2 as being an oxidizer unless it's a metal fire. What's special about metals? If you look at the chart, it's very easy to see what's special about metals. Yeah, all the metals are strong. In fact, the most powerful reducer is lithium, a metal. All the metals are very strong reducers. And so CO2 is powerful enough to react with metals. And so if you were to use CO2 in a metal fire, that would be like fanning the flames. That would be like trying to get it to burn more intensely. And so you wouldn't want to do that. But, that's the redox properties. But did you know that CO2 is an acid? It doesn't look like an acid. This is a Lewis acid. What is a Lewis acid? A Lewis acid is an electron pair acceptor. And so what would make CO2 want to gain electron pair? So what we usually do is we look at the Lewis structure, like this. And then there are different ways we can analyze. The way you know how to analyze structures like this is by determining what? Oxidation numbers. So what are the oxidation numbers here? +4, -2, -2, which tells me that the carbon is electron poor, but not severely, because if it were severely electron poor, it would really want electrons, and it would be a powerful oxidizer like O2, F2, H2O2. But +4 doesn't seem so bad for CO2. But nonetheless, if you were an electron pair is negative charge density or positive? Electrons are negative, right? And so if you're an electron pair, which of these atoms would you be attracted to? If you were negative charge, you'd be attracted to carbon, right? And so what we say is that carbon would be like the active site for its acid-base properties. If a base, which is negative charge density, attacks this acid, which is positive charge density. All acids have positive charge density, whether they're Bronsted or Lewis, right? Is H plus. So if your base, negative charge density, positive charge density, you're going to come together here. And so in a Lewis acid-base reaction, we just look. Okay, water is amphoteric. Water can go either way. Like this. Water has an electron pair, so if water acts as a base, what's going to happen? What's going to happen is there's going to be a collision here. Boom. This is a good favorable. If the oxygen collides with an oxygen, they're going to repel each other, right? Bounce off. But if this hits here and collides with that carbon, something could happen. But can carbon have more than an octet? No. And so what happens is that too many electrons, some electrons have to get pushed out. So these electrons get pushed out of here. And so let's imagine a collision occurring where, boom, this electron pair gets pushed in here, this electron pair gets pushed out, and we create this. Okay, look at that Lewis structure and tell me, is there anything wrong with that Lewis structure, or does it look okay to you? Look okay? Or something wrong? All right, what do you do when you're looking at Lewis structures to determine if they're looking all right or not? Huh? Doesn't it have to do angles? Don't ignore angles. Lewis structures, nobody cares about the angle. This is not 90 here. This is actually 120. You know, this is actually 105, 109. You know. But I'm not drawing it accurately. Lewis structures, people don't draw accurately. So what do you do when you're looking at Lewis structures? You look for octet. Does everything have an octet here?
Yeah.
Yeah, so it's good, right? Is this Lewis structure good? This Lewis structure look good to you?
No.
Everything has an octet. So what's wrong with it?
It's not the maximum charge. I mean, those electrons are pulled to oxygen. -1 oxygen.
If you look at the oxidation states did not change. All the oxidation states are the same as before. So what is wrong with this, if anything? Or does it look good?
Carbon loses its electrons to all the oxygens.
Yeah, so carbon stays +4. Nothing changed. It was +4 here, it's +4 there. You look at all the oxidation states are the same. Oxygens are -2, hydrogens are +1. Nothing changed. What oxygen? This oxygen is -1? Or is this -2? Oxidation state. Oxidation state is still -2. Right? So what's wrong with it? Or is it -1? Did you cover formal charge in Chem 4?
Yeah.
Yes? It's been a while, so you probably forgot. I didn't bring up formal charge because I don't want to mix you guys up. There are 3 ways of counting electrons, right? The 3 ways of counting electrons in a structure are octet, right? Oxidation state, and formal charge. Oxidation state is summarize oxidation state for me in one sentence? When you're counting up the electrons using oxidation state, how would you describe the counting system?
How many?
You guys are reviewing your notes, right?
Yeah.
Maybe you need to review more frequently, or at least review the book or whatever you do. Reread the chapter. But oxidation state is, the thing is, this is the next thing you should do. The next thing you should do is not memorize what somebody told you, the definition of the oxidation state. You need to put it in your own words. Think about how you would describe oxidation state to somebody. You could read the dictionary definition, and you can recite that verbatim, for every single word. But do you do that? No. Usually you come up with your own little definition of a word, right? Well, that's the same thing you need to do with these words. Oxidation state is what in your own definition?
The electric stability of
that. Not electric stability. That's how we use it to determine stability, right? But what is it exactly?
When the electrons are missing or leftover.
Okay, that's good. Oh, that's a nice definition. If the electrons are missing or
You're missing one.
extra or whatever.
Yeah.
Yeah. Well, you could say if they're missing or they have extra electrons by just saying it's the charge. The charge tells you if it has extra electrons or if it's missing electrons quickly. A +1 charge tells you it's missing. A -1 charge tells you gain an extra electron. And so oxidation state is a charge, right, on an atom in a structure.
Is it the same kind of electrons?
With a counting system. What's a counting system for oxidation? How do we divvy up the electron? You see, when we count octets, we look at oxygen has all 8 electrons. That's an octet, right? Carbon has all 8 electrons. That's an octet. It's when we count octets, the atoms, you're just looking at how many electrons surround the atom, not necessarily how many belong to it. When we count oxidation state, we're counting how many electrons belong to that atom using a system. What's our system? Winner takes all, right? Winner takes all. So oxygen wins. That means carbon lost. Winner takes all. That is counting electrons using oxidation state. Counting electrons using oxidation. There's another counting system that we use for Lewis acid bases, and that's called formal charge. Formal charge is just the opposite. It's not winner take all. Formal charge is let's share 50-50. That's formal charge. And so when we look at formal charge, you're absolutely right. Let's share 50-50 means that there are 2 electrons here. That means oxygen gets one and carbon gets the other. And so in terms of formal charge, the formal charge on this oxygen is -1. We show formal charges with circles like this. And so that would be a -1. Look at this oxygen here. Well, if we look at the carbon, the formal charge on carbon is 0 because it has 4, it's supposed to have 4. On this oxygen, what is it? 0 because it's got 6. On this oxygen, it's a little different. This oxygen is +1, missing 1. And these hydrogens are 0 and 0. And so formal charge, oxidation state is winner takes all. Formal charge is let's split it down the middle, right? Split it down the middle. You never, ever compare formal charge with oxidation state because that's like comparing apples with oranges because they mean totally different things, right? And so this is just another way of analyzing the structure. In other words, let me put it into scientific jargon. Formal charge, we're assuming 100% covalent bonding. Oxidation state, we assume 100% ionic bonding, unless they're even. And so the problem with this structure is the formal charge. This oxygen gained an electron, this oxygen lost an electron. Why would one gain, the other lose? It doesn't make sense. So this is unstable. Now, imagine this. Are these structures, somebody mentioned about the bonds and angles and that stuff, but that's true. We got to look at that. And we also have to look at rotation. There's free rotation about single bonds. So this thing's rotating up here. And it's vibrating too. And so what can happen is this. What can happen is if this thing rotates in such a manner, and actually it's more like this. This thing rotates to this side, and we have this oxygen over here, like this. This is negative, this is positive over here. Then we got this double bond over here. So these molecules are not static, they're dynamic, they're always moving. And so what can happen is this. I'm spending too much time. This pair of electrons get pushed into this hydrogen, knocking this pair of electrons out. And so it's vibrating like this. Do you think these molecules at room temperature vibrate all at the same frequency? No. There are going to be some that are going to have higher energy vibrations, right? Boom! You have a high energy vibration that knocks the hydrogen off the oxygen. The hydrogen goes to this oxygen.
Why is that?
Why is that?
So you make the formal charge 0.
Right. Because take a look at what happens. If that happens, we'll end up with this. Okay, that picks up the proton, leaves the electron pair, so we end up something like this. Do you recognize this molecule? H2CO3, which is called carbonic acid. And so, do you think, these kind of collisions, do you think these are common collisions or difficult collisions? Yeah, difficult collisions. So let me erase this here. And so the net reaction is this. If we take CO2 and water, this is going to form carbonic acid, but, it's not that probable. So we don't form much, just a tiny bit. In fact, carbonic acid is something we call unstable. That should decompose into CO2 and water. And so this is much, much more favored. But nonetheless, it's true. So if you take a straw and you blow into water, you know what you're going to form a little bit of? Carbonic acid. You're going to make the pH of the water drop down. And this is the reason why our DI water, if you ever measure the pH of our DI water, do you know what it is? What's neutral? pH what? 7. Our DI water is pH 5.5. Yeah, that's bad. It's bad because it's acidic. Our DI water is not supposed to be acidic. Why is it acidic? Because we store it up in a tank upstairs, and the tank is exposed to air. And the CO2 from the air gets into our water and makes it acidic by forming a tiny bit of carbonic acid. The way to get rid of the carbonic acid is we take our DI water and we throw it onto a burner and boil it. If you boil the DI water, you're going to drive off the CO2 as a gas. So you could decompose the carbonic acid that way. It normally decomposes, but a little bit of residual carbonic acid stays in there, makes the pH a little bit acidic. If we want pH neutral, DI water, we would do that. Okay, so in Chem 4, you might have learned that non-metal oxides are acidic. Non-metal oxides plus water make acids. And the same thing, what do you think SO2 in water form? Sulfurous acid. What do you think SO3 in water form? Sulfuric acid. What do you think NO2 in water form? Nitric acid. All these are Lewis acid-based reactions. And it's the same kind of thing. Nitrogen is electron deficient. All these are to some extent. All right, now you might have heard this. Metal oxides are basic. But metal oxide, oxide's already a base, right? A good base. And metal oxides like this aren't very soluble, but a tiny bit will dissolve, and that tiny bit will form actually more than a tiny bit dissolves in this. If we have calcium oxide, it pretty much goes to calcium hydroxide in this reaction. We can convert the oxide to hydroxide. Oxide's a powerful base. Hydroxide is less powerful. Right. So we're going from stronger base to weaker base, etc. So these are Lewis acid-base reactions. We'll talk more about Lewis acid-base reactions when we get to Lewis structures. So I need to start with chapter 6 next. Let's take a look. And behind schedule. Chapter 6 deals with the gases. So this is, in some ways, this is similar to Chem 4. In other ways, this is different. And so what's new for gases? What's new is more on gas pressure and liquid pressure. That's new. What's new for gases is gas mixtures. You did very simple gas mixtures in Chem 4. We're going to do a lot of mixtures, and there's more than one way of looking at mixture. And this always trips students up. And what else is new is the limitations of the ideal gas model. Is there such thing as an ideal? You've heard of the ideal gas law, right? Everybody has. Is there such thing as an ideal gas? Does an ideal gas actually exist in nature? No. Gases deviate from ideal behavior, and you have to know, is it a significant deviation or just a minor deviation from ideal behavior? And so let's take a look at pressure for, when we think about gas pressure is usually, some kind of force per area, just applying some force per area. For gases, the force is going to result from these collisions, right? You got A, and then this could be a mixture, B. We got collisions with the surface, and those collisions create the pressure. And so we have that. Another way of thinking about pressure is kind of a weight. You have the weight. Weight is like a force, weight on some area. And so the first pressure we're going to look at is atmospheric pressure. atmospheric pressure, what is the pressure today, roughly? 760. I wonder if we can figure out. I have a pressure gauge. I need to bring it in, but let's say today's barometric pressure. Pressure. Torrent. Actually, you know what? I didn't even check to see if this has it. Here it is. 29.83 inches is today's pressure. 29.83 inches. Is that a lot of pressure? So, what do you visualize when you see something like 29.83 inches? What comes to mind? I mean, what do you visualize physically happening? Anything? Yeah, well, this is what I visualize. Let me tell you what I think of. I think of this. I think of me here, and then I have the weight of the air above me. And so to blow this up, let's say here's some mountain, then we're down here at sea level or something. But then I have air. Air is going to be most dense down here, right? And as you get higher and higher, it decreases. And so I have this blanket of air above me, and this blanket of air is going to weigh a certain amount. Do you know how much it weighs?
More than up top.
Well, you know, the weight of the air here pushing down on me would be equivalent to the weight of 29.83 inches of mercury. So if I was in a mercury, like a mercury swimming pool, which you wouldn't be in a mercury swimming pool, but if you were in a mercury swimming pool, you know, and you were on the surface, right, you wouldn't feel much pressure. But as you dive deeper, you feel more pressure, right? And so the deeper you go, the heavier that mercury above you becomes, and the more pressure you feel. So you would have to dive about 30 inches deep into the mercury to get that equivalent weight. Does that make sense? And so this would be, if you're in a mercury pool, 30 inches deep. That would be the equivalent. This is called liquid pressure here. So 30 inches of mercury, liquid, on top of you. Well, how would that feel like? Let me grab something here. Where are you? Sorry, I'll have to let you know how that would feel like when the mercury has disappeared from back there. All right, so this is the way we measure liquid pressures. You know, the pressure of a liquid equals rho GH. Okay, we'll use rho GH. Rho GH. This is from physics. Rho is the density of the liquid. G is the gravity, force of gravity, which will be a constant right around here. H is the depth, you know, the height. Just say the height.
Are we gonna be using that for?
Yes. And so, does the density of mercury change? No. Does the force of gravity change? No. And so, basically, the only thing that changes, that is going to vary the pressure of liquid, is the height or the depth we go under. And so, if you're under 10 feet of mercury, you have enormous pressure because you got all that mercury above you. Just like I was reading, you know what the world's deepest swimming pool is? In Italy. Did you hear about that?
6,000 feet.
Not 6,000. No, that would be really deep. 131 feet.
How much?
131 feet. I think it was 131 feet in Italy. Did you hear about that? And so there's some videos of people sinking way down there, like 100 feet. But can you imagine 100 feet of water or 130 feet of water above you? You know, what would the pressure be? That pressure would be pretty enough to do some. I think so. I mean, definitely enough to do some damage. So what we're going to do is let's go ahead and calculate these pressures.
Is there like 4 atmospheric pressures at the bottom?
Let's calculate it. We're going to calculate it right now because it's an easy calculation. So let's assume that this pool in Italy is at the surface of the Earth here. And so what is the weight of the atmosphere on a normal day? Weight of the atmosphere is about 1 atmosphere, right, on a normal day. And then we have this pool. And this pool sinks down 131 feet. 131 feet. And so if I were able to dive to the bottom of this, I'd have 131 feet of water on top of me. And that's going to weigh a lot. And so let's calculate the pressure here. And so what we're going to have is not only do we have the weight of the atmosphere pushing on the top of the pool, we're also going to have the weight of all that water pushing down on us. And so what we're going to do is we're going to add up the two weights. So the weight of the atmosphere, 1 atmosphere, plus the weight of the water. Now let's figure out the weight of the water here. The weight of the water is going to be, or the pressure of the water. And so here is the pressure of the H2O liquid, and this is going to equal the pressure of the air here. And so the pressure of the H2O liquid, let's go ahead and calculate it. The pressure of the H2O liquid is easy because it's just equal to rho GH. Our book has DGH, I think. D for density. So going through this calculation, what is the density of water?
1,000 kilograms per meter.
We'll just do 1.00 grams.
Per centimeter cube.
Okay, G is 9.8
Meters per second squared.
meters per second square, and H is 131 feet. Now we look at the dimensions here and go, wow, these dimensions are a hassle, right? Grams per centimeter cube? Yes, thanks. Grams per, let's go with grams per milliliters. Thanks. So these units don't seem to work out, do they? No, they don't. And in fact, these are different than this. You know, because the pressure of the air at 1 atmosphere, you've already memorized, this is going to be 760 millimeters of mercury. And so they're going to be different things. Since we express pressures and heights, you know, the height of a mercury column, what we're going to do is we're going to change the height here. This is the height of a water column. And so one thing we could do is we could just go ahead and calculate. Do you know what the SI unit of pressure is?
Pascal.
The SI unit of pressure is Pascal. So we can convert this, the height of the mercury, into pascals by multiplying it by rho and g. If we can do rho g, because what a pascal is it's a kilogram. What is it? Meters squared per second squared. If we do that, then what we're going to get is we're going to get the pascal. But we aren't going to do that. What we're going to do is we're just going to do this. If I have 131 feet of water, that's going to weigh a certain amount. That would give us how many feet of mercury? You know, it turns out that mercury is much more dense than water. And since it's much more dense than water, I don't need as many feet of mercury to weigh the same amount as 131 feet of water. Does that make sense? And so all I'm going to do is I'm going to just do a simple conversion. And the simple conversion is this. If I'm interested in how many feet of mercury liquid would be equivalent to 131 feet of water, then we could solve this equation using dimensional analysis. But we're just going to do an intuitive equation. The intuitive equation is going to be this. I got 131 feet of water. And so for every foot of water, or for every foot of mercury, how much water do I need? Well, look, I'm going to do that. I'm going to do for every 1 foot of mercury, how much water will I need to weigh the same amount? And so what I'll need the density of mercury. And so let's see what the density of mercury is. I'm going to go over here. And I already should have the number memorized, but I don't.
Yeah.
13.59. So mercury is 13.59 times more dense than water. And so for every 1 foot of mercury, I'd need 13.59 feet of water to weigh the same amount. Does that make sense? And so what this gives me is, actually I didn't bring a calculator. Someone calculate? 9.64 feet of mercury. All right, so being under 131 feet of water would be the equivalent to being under 9.64 feet of mercury. Wow, that pressure is tremendous, because if you know how much mercury weighs, I mean, that's crushing pressure there. All right, now if we're under 9.64 feet of mercury, how many millimeters of mercury is that? And so we'll just convert it to millimeters. So 9.64 feet times 12 inches per foot times 2.54 centimeters per inch gives us times 10 millimeters per centimeter gives us how many millimeters of mercury? 2,938 millimeters of mercury. All right, so now if we dive to the bottom of this pool, and the atmospheric pressure that day is 760 millimeters of mercury, and the water itself is 2,938 millimeters of mercury, then we're under a total pressure of, add those two up together.
3,698.
So P total is 3,698 millimeters of mercury. Now convert that to atmosphere. So divide that by 760.
It's around 4.8 atmosphere.
4.8 atmospheres. Can you imagine that? You know, if I go like 9 feet deep underwater, it's too much for me. But 131 feet, that's... Well, anyway, well, they have those free divers that hold their breath for like 5 minutes or something.
They don't do that. They usually have diving gear on.
Watch the video. They have it on YouTube. I don't know if they go I haven't seen, but they go pretty deep. I mean, it's over 100 feet that they're going. It looks like holding their breath. I don't know. They're just used to it, I guess. All right, we'll stop here and.